Okay, so L'Hopital's rule, it is something that is going to help us with certain limit problems. So it's been a while since we've talked about limits, so I want to remind you a couple of things. So recall, we write the limit of f of x as x approaches a equals L if f of x approaches L as x approaches a. I mean, we know this, but I just want us to get into the right mindset. Uh, we had a full definition of the limit earlier in the semester, and this is just kind of the short version of that definition. Let's see, we could also remind ourselves that a limit can be defined even if f of a is not. And we saw that visually with some examples earlier in the semester where we would have a graph with a hole in it, and maybe the hole in it means that the function is not defined at that point, but the limit could still be defined. Or not, sometimes it is, sometimes it isn't. And informally, we can think of the limit as x approaches a, f of x, as the y value that the graph approaches. As x gets closer and closer to a. Now, that's kind of the informal version. Earlier in the semester, we had the official definition. We went into some more detail about what it means to get close to something and what does this word approaches mean. We said arbitrarily close, things like that. So we talked about limits really at the beginning of the semester, back before we even knew what the derivative was. And now we're going to see a technique involving derivatives that's going to help us solve some limits. So in a way, it's like we've come complete circle because we learned about limits to help us define the derivative, and now we're going to use the derivative to help us do some limit problems. All right, so let's go ahead and let's look at an example of a limit that we did a long time ago. I think this is exactly a problem that we've seen before. If not, it's definitely the same form as some problems we've seen. The limit as x goes to 1 of x squared minus 1 over x minus 1. And I'm not exactly showing you L'Hopital's rule yet. We'll get to that pretty soon. But how would we deal with this in the beginning of the semester when we first saw limits? I mean, you say, okay, x is approaching 1. You might think about what's happening to the numerator and what's happening to the denominator. Well, if x goes to 1 in the numerator, then the numerator looks like it's going to 1 minus 1, which is 0. And in the denominator, it also looks like it's going to 1 minus 1, which is 0. So I'm going to say that this looks like 0 over 0. Looks like is not a very formal mathematical term, but we've seen limits like this before, and we know that it might actually equal something if we factor and cancel. So that's how we dealt with this. We factored and canceled. We said, hey, that numerator factors into this. And then once you factored it, it's okay to cancel those terms. Limit as x goes to 1 of x plus 1. It's a lot simpler now. And this thing right here is a polynomial. It's a simple polynomial. We had a theorem back then, or a rule back then, that said if you are left with just a polynomial, then at that point it is okay to just put in x equals 1. And that's because polynomials are continuous across all real numbers. So this does equal 1 plus 1, which is 2. So the thing that I wanted to draw to your attention is that at first glance, this problem kind of looked like 0 over 0. And it's tempting to just say, oh, well, that's undefined. You can't divide by 0. Look at the denominator. It looks like 0. However, remember, limits say that x approaches a. So x is approaching 1, but it's not actually equal to 1. There's a difference, right? It's getting closer and closer to 1, but it's not really 1. So the denominator is not really 0. And in fact, this whole thing evaluates to 2. I'll show you another one. Remember we had a lesson about limits involving infinity? How about one where x approaches infinity? We saw limits that looked something like this back in that lesson. Whoops, let me move the page up. Now, infinity is not a number. Infinity is sort of a concept that x can approach, but x will never actually equal infinity. Infinity's not a number that I want to see you just substituting in for x. Don't say infinity squared, right? But we can imagine that x is growing arbitrarily large. X is a million, a billion, a trillion. It keeps growing and growing. So what's happening to the numerator and what's happening to the denominator? I would say that this looks like infinity over infinity. Maybe I should put these in like quotation marks because these are sort of it's not really 0 over 0. It's not really infinity over infinity. But that's just what it looks like at first glance, because I'm imagining this numerator, x squared. If x gets incredibly large, then x squared gets incredibly large. The minus 1 is pretty insignificant. And then on the bottom, the x squared gets incredibly large. The little plus 1 is pretty insignificant. Yeah, it kind of looks like both the top and the bottom are approaching infinity. But we learned back then that there are rules for how to deal with this. We actually learned a shortcut based on the degree of the numerator and the degree of the denominator. Right? And you could just use that shortcut, and I think you know what the answer to this is. But I'll show you how you would do it with algebra without the shortcut. Just to remind us of why does that shortcut even work? Shortcut is you take the coefficient in front of x squared here, coefficient in front of x squared here. I think the answer is going to be 1 over 2. But why does that rule work? It's because you could use algebra, multiply by something over itself. If you multiply by 1 over x squared over 1 over x squared, you get this. I think we did something like this just for one example back in that lesson. I'm doing it again now. This kind of algebra. The point of this is that now x is approaching infinity, so 1 over x squared, that term is approaching 0, and this 1 over x squared is also approaching 0. So overall, I'm getting 1 minus 0 over 2 plus 0, and that's why the answer is 1/2. That's why that shortcut works, because of algebra steps like this. So what do these two examples tell us? Why am I revisiting old limit problems? I guess I wanted to say that even if at first glance a limit looks like 0 over 0 and you're tempted to say it's undefined, or it looks like infinity over infinity and you're tempted to say, well, I don't know, what would you say? Would you say that's undefined? Would you say that equals 1? Well, in fact, it equals 1/2, and this one equals 2. So the point is, you can't always tell what a limit is going to be based on, a quick glance like that. You can't just imagine substituting in 1, because that's not how limits work. All right, now these limits, these types of limits have a name. These types of limits, which I'm going to say are of the form 0 over 0 and infinity over infinity. That's kind of the category. That's kind of the type of limit that we're talking about. These are called indeterminate forms. These are limits that are indeterminate forms. And this discussion we've had so far shows us that we already know how to deal with some limits that are indeterminate forms. We did it back in the beginning of the semester, either by factoring and canceling, or by using algebra or rules to help us deal with these situations. So we already know how to deal with some limits that are indeterminate forms. The point of this lesson is that as of right now, we don't know how to solve all indeterminate forms yet, and we need an extra tool to help us with some of them. I'll show you one. I'll show you one that we're actually not ready to solve yet, but we'll be able to solve very soon, in a few minutes. What if you had the limit as x approaches 1 of ln x over x minus 1? Okay, so we could think about the top and the bottom, like what's happening to the numerator and denominator. As x approaches 1, the denominator looks like it's approaching 0, 1 minus 1. The numerator looks like it's approaching ln 1. Well, ln 1 is 0, right? We know ln 1 is 0 because e to the 0 is 1. So I'm going to say that this is, instead of using the phrase looks like, I'm going to say this is an indeterminate form of the type 0 over 0. Okay, instead of saying looks like, we use the phrase indeterminate form. So up above, we solved some limits that were indeterminate forms. How are we going to do it for this one, though? We can't just put in x equals 1. We know that. We would get 0 over 0, and we know that that doesn't work for ones like this. We don't just put 1 into the expression. However, with this problem, the issue is that we can't really rearrange, factor, or simplify. I don't see any kind of factoring or simplifying or algebra trick that's going to help us this time. We need a new trick to help us with limits like this, when there's no factoring that can be done or anything like that. Oh, by the way, didn't we also deal with some limits back then by multiplying by a conjugate over a conjugate? I guess that was another algebra trick, but that's not going to help us here. There's no square roots. So the new trick that's going to help us with some indeterminate form limits, it's going to be called L'Hopital's rule. So this is a French name. It has an apostrophe after the L, and it has an accent over the O. L'Hopital's rule. And I've also seen it written as this. So, I mean, either one is fine. I'm just telling you in case you see it written in two different ways in a textbook or the internet or whatever. And it says, if a limit as x approaches a of f of x over g of x is an indeterminate form, of the type 0 over 0, or I guess you could say above the two indeterminate forms that we talked about were 0 over 0 or infinity over infinity. It could actually be plus or minus infinity over infinity. I mean, if it was minus infinity over infinity, then we'd still have the same kind of issue. All right, then L'Hopital's rule is actually going to be just a really nice formula. And it's not something that's hard to memorize. It's actually just going to tell us what the limit is. You should be expecting that it's going to use the derivative at some point, because I said this was going to be an application of the derivative. The limit that we are trying to evaluate, the limit of something over something, so there's like a numerator and a denominator function. All right, ready for this formula? It equals the limit as x approaches a of f prime of x over g prime of x. Yeah, the derivative of the top and the derivative of the bottom. I do have to say, provided that this second limit exists or is infinity or negative infinity. That's just a little disclaimer. But yeah, this is L'Hopital's rule tells us that if you have one of these indeterminate forms, which they seem pretty common with limit problems, a lot of limit problems are in these kinds of forms, that one way that you can solve them is actually you still have a limit. All right, the limit of this equals the limit of that. So you still have limit as x goes to a, but you take the derivative of the top and derivative of the bottom. And that's not very hard to remember. I mean, derivative of the top, derivative of the bottom. It's not a complicated formula. So note, this rule also works for one-sided limits. And limits at infinity. So I wrote the formula above with x approaches a. And I guess what I'm saying now is it also works if x is approaching a with a little plus sign, if x is approaching a with a little minus sign, if x is approaching infinity, and if x is approaching negative infinity. The same formula, just change x approaches a. It also works. So now what I'd like to do is I'd like to answer that question from before. And we're going to apply L'Hopital's rule because I said it didn't look like there was any factoring or algebra. And the whole point of this is we needed this new trick. So let's try it on this problem. This will be our first L'Hopital's rule problem. Okay, well, we already identified that this was an indeterminate form, but I'm going to write it again. I'm going to abbreviate it. Indeterminate form of the type 0 over 0, which means we can use L'Hopital's rule. I want to point out to you before I move this off of the screen, L'Hopital's rule is stated saying if the limit is an indeterminate form, then you can use this formula. So we don't use this formula necessarily for every limit in the world. We use it for these types of limits, which this is. So let's use it. It says that this equals the limit as x approaches 1 of the derivative of the top over the derivative of the bottom. Now, when you take derivative of the top, derivative of the bottom, that changes the function. Like ln x over x minus 1 is different from this function now, right? So as functions, they are not equal to each other. But as limits, they are. The limit of this equals the limit of this. So let's do this. We know these derivatives. Derivative of ln x is 1 over x. Derivative of x minus 1 is 1. So this whole thing simplifies to this. What happens to 1 over x as x approaches 1? It just becomes 1 over 1, which is 1. All right, so that was us applying L'Hopital's rule to solve this problem. This limit actually equals 1. Let's do another one. The limit as x goes to 0 of 3 to the x minus 2 to the x over x. First of all, is this an indeterminate form? Is there some other way we can do this? Well, let's see. Think about what happens to the top and bottom. The bottom definitely goes to 0. The top goes to 3 to the 0 minus 2 to the 0. Well, that would be 1 minus 1. So yes, this is an indeterminate form of the type 0 over 0. So L'Hopital's rule does apply, meaning this equals the limit of d dx of the top over d dx of the bottom. These two limit problems. These are ones that I couldn't really give you at the beginning of the semester because we didn't have this trick yet. And we couldn't really talk about L'Hopital's rule back then because we didn't know about derivatives yet. So that's why this fits in perfectly here. The derivative of the top is 3 to the x ln 3, and then minus 2 to the x ln 2, and the derivative of the bottom is just 1. Exponential functions are continuous, so it is okay to just plug in 3 to the 0 and 2 to the 0. So this is 3 to the 0 ln 3 minus 2 to the 0 ln 2. Notice that I didn't write limit in front of this step because we've already evaluated the limit. You should put equal signs between expressions, and you should write limit in front of limits, but I'm not writing it here because we already dealt with it. This is ln 3 minus ln 2. Is that the answer? Yeah, I mean, that's basically it. I guess one thing we could do that might make it look a little simpler is, remember a little property of logarithms that says you can combine this? I like that for this answer. Logarithm minus a logarithm, you just combine it into that. That's the answer. And wow, looking at this problem, I think we really couldn't tell. Like, at first glance, you might look at this and say, it looks like 0 over 0. I don't know what it's going to be. I would not have guessed that the answer would be this, ln of 3/2. It's some kind of decimal. It's around 0.4. But yeah, it's a real number. Notice both of these problems we just did were indeterminate forms of the type 0 over 0, but we get different results. So just because it's in the same form doesn't mean you're always going to get 1, for example. You know, the 0 over 0 form can lead to different results, different answers. We should look at some infinity over infinity examples. I want to show you an infinity over infinity example from earlier. Actually, we did this today, but I want to redo it using L'Hopital's rule to show you that this also works. So it was the limit as x goes to infinity of x squared minus 1 over 2x squared plus 1. Now, I can think of 3 ways to solve this. All right. Number 1, we could use that shortcut. Coefficient in front of x squared, coefficient in front of x squared. The answer is 1 over 2. That's the first method. Method number 2, do what we did earlier in this video and do some algebra. We multiplied by something over something, and yeah, we also got an answer of 1/2. Method number 3 is L'Hopital's rule, because this is, I'm just going to actually say it's an indeterminate form of the type infinity over infinity. Indeterminate form of the type infinity over infinity. So yeah, we could do this with L'Hopital's rule. Actually, you know what? I'd like you to try doing this with L'Hopital's rule. You could pause the video for a moment and give it a shot. All right, so we do limit of the top, derivative of the top, I should say. I mean, we know what the answer is going to be. We know it's going to be 1/2. But I wanted to show you that this is another way to deal with these kinds of problems. Derivative of the top is 2x. Derivative of the bottom is 4x. The x's cancel. We wind up with 2 over 4, and 2 over 4 simplifies to 1/2. So now this is a new way for us to solve these kinds of problems if we want to. Multiple ways to get to that answer. I'll show you a tougher one. Let's do it. Let's do a new one. I'll do this one for us. How about we want to evaluate x goes to infinity of e to the x over x squared. It's not really that tough, but I'm going to do this because something a little bit different is going to happen. So whether you call it the form or the type, you identify that this looks like an infinity over infinity case. So we want to use L'Hopital's rule. We're going to do the limit x goes to infinity, d dx of the top, d dx of the bottom. And what do we get? Well, these derivatives are not that hard. This is e to the x, and this is 2x. But what happens now? What happens now? What do we do? We did L'Hopital's rule. In the previous problems, when we did L'Hopital's rule, we got to the answer pretty quickly after that. This time we did L'Hopital's rule, and we still are wondering, like, well, what does this equal? Let's think about what happens to the top and bottom. The top is going off towards infinity. The bottom is also going off towards infinity. So what's happening here is we still have an indeterminate form. And how do we deal with indeterminate forms? We use L'Hopital's rule. So we're going to use L'Hopital's rule a second time. Derivative of the top, derivative of the bottom. Now, you might be worried, are we stuck in some kind of loop here? Are we going to be doing L'Hopital's rule over and over again? But actually, I think that this is going to work out because we started with a problem that had x squared on the bottom, and then we got to a problem that had 2x on the bottom. And now I think we're going to get to a problem that just has a 2. So it feels like the problem is getting simpler. It feels like it's headed in the right direction. Actually, look at this. This is not an indeterminate form anymore because the bottom is just 2. In fact, that 2 you could pull out front as like a 1/2. So 1/2 limit x goes to infinity, e to the x. Yeah, e to the x is approaching infinity. The multiplying by 1/2 or dividing by 2 is not really going to stop that. So the answer is infinity for this one. So there are 2 things that we can learn from this problem. First of all, we learn that sometimes you have to apply L'Hopital's rule more than once. We used it here, and we used it here. And the other thing to learn is that sometimes these answers could be infinity. You know, they could be infinity or negative infinity. Sometimes you could even have a problem where you might need to use L'Hopital's rule 3 times. Or four times. I don't know if we'll see any that need it 4 times. It's basically because of this x squared here. I guess if this problem had an x cubed, then we would probably need to use L'Hopital's rule a 3rd time. All right, let me give you one to try. I want you to try this. The limit as x goes to infinity of 3x squared plus e to the x over e to the x plus 1. So pause the video and give that a shot. Okay, so, yep, this is another infinity over infinity case. Indeterminate form. So we want to take derivative of the top, derivative of the bottom. I'll show you a little trick. Sometimes when we do L'Hopital's rule, this is up to you if you want to write it this way or not. But sometimes, instead of writing the d dx's, let's just do the limits. I mean, do the derivatives. Like 3x squared, I know that's going to get me 6x. E to the x is the derivative of itself. The bottom is e to the x. So I took the derivatives, and sometimes in order to indicate that we used L'Hopital's rule, sometimes people will write a little L apostrophe H over the equal sign to indicate that in this step I applied L'Hopital's rule instead of writing the d dx's. I like that. I do that sometimes. I think it's a pretty cool little notation. Oh, wait, what do we need to do now? So look at this. 6x plus e to the x over e to the x. You could say that this is still an indeterminate form, and you could use L'Hopital's rule again. I see two different ways that we could deal with this. All right, how about this? One way, and you might have done it this way, is apply L'Hopital's rule again. So what's the derivative of 6x? That's 6. We get this. Looks like the numerator is going to infinity and the denominator is going to infinity. We could apply L'Hopital's rule again. And we get e to the x over e to the x. Ah, well, this is also an indeterminate form, right? It's infinity over infinity case. And you might say, well, wait a second. If I apply L'Hopital's rule to this, like, it's just going to equal itself. We're just going to keep being in a loop, getting this like, over and over and over again. Well, here's the thing. E to the x over e to the x is 1. So don't apply L'Hopital's rule. Just say something divided by itself is 1. So the answer is 1. So that's one way to solve this. I saw another way to solve this that I think I'm going to show you. I did L'Hopital's rule at the beginning, and then from here I kind of branched off and did some other steps. And I want to show you that this also gets us 1. I saw this expression and I said, hey, you know what? There's an e to the x on the bottom. There's an e to the x up top. It might actually work out nicely if I split this up. So I split it up like this. The nice thing about doing that is you get this. You get kind of a 1, e to the x over e to the x. And then what did I do? I guess then I said, this is the limit of 6x over e to the x as x goes to infinity, plus the limit as x goes to infinity of 1. Like, you can split up limits, right? Limit of the first piece plus the limit of the second piece. Then I applied L'Hopital's rule to the first term. I don't know, should I put the apostrophe LH here? Yeah, I guess I should. We're applying L'Hopital's rule just to this first piece. So I got a 6 over e to the x. And that other limit is just 1. So let's just put 1 here. And then I said, okay, this piece, 6 up top, e to the x on the bottom. As x goes to infinity, the bottom is going to grow incredibly large, astronomically large, while the numerator is just a tiny little number 6. So that whole thing is going to approach 0. And then we still have the plus 1, and I got 1. So that's two different methods, I guess. The method up top, you know, the method up top where we use L'Hopital's rule 3 times, that's pretty straightforward. There's nothing wrong with that. I just saw this as another way to do it. I guess I wound up using L'Hopital's rule twice with this method.